These are the notes for section 8.2. This is day 1, and the topic is integration by parts. So we have a product rule for derivatives, which says if I need the derivative of a product of two functions, then I just can take the first times the derivative of the second plus derivative of the first times the second. Well, do we have something like that for antiderivatives? In other words, can we take the antiderivative of the product of two functions? Well, not quite. We do have this formula here, which helps. And the difference is that in our two functions, we will have one function and the other one will be the derivative of a function. The proof of this is based on the product rule that you see sitting here. So we know it works because we know the product rule works. So if I start with the product rule, the derivative of two functions multiplied is first times the derivative of the second plus derivative of the first times the second. And if I take that entire statement and take the antiderivative of both sides, we still have a valid statement. So to make it a little bit clearer, dv dx is written as v prime, and du dx is written as u prime. When I take this antiderivative and send it to all terms, the antiderivative of derivative cancels out, and I'm left with uv. This statement here, the antiderivative of u v prime dx, and the antiderivative of v u prime dx. V prime is dv dx, so the dx in the denominator cancels with dx, and we're just left with dv. Over here, u prime is du dx. The dx here cancels with the dx down there, and we're left with just du. So now the statement becomes uv is the antiderivative of u dv plus the antiderivative of v du. We're going to solve for this term here. So when I bring the final term to the other side, we get the antiderivative of u dv equals uv minus the antiderivative of v du. Okay, that might sound like a whole lot of nonsense, but in a second, when you see this applied to two functions, it'll start to make sense. So every time you do integration by parts, I would strongly suggest that you write out this formula so that you get it memorized. And how do you know when to use integration by parts? Well, if you see two functions, it's probably a good candidate for integration by parts. I'm going to call this x the u function. I'm going to call e to the 2x dx the dv function. And you'll see that u needs its derivative, du. The derivative of x is just 1, so du equals dx. And the dv section needs the antiderivative so that we can find v. So if dv is e to the 2x dx, the antiderivative is 1/2 e to the 2x. And what you should do is double check by taking the derivative of this and making sure that you get that. So now that we have these four things, we can take and substitute them into the formula. So my u dv is equal to uv minus the antiderivative of v du. U is x, v is 1/2 e to the 2x minus the antiderivative of 1/2 e to the 2x dx. And you notice we can do this antiderivative because now there's just one function. Before, when we had two functions, a u function and a dv function, now we just have one. The 1/2 would move out front, and the antiderivative of e to the 2x dx, well, we just did that here, is another 1/2 e to the 2x. Tack on your plus c, multiply the fractions, and you get the final answer right here. Second example, very similar. Again, I see an x, it happens to be the second thing, but this time I'm still going to call u as x so that du is dx, and the antiderivative of cosine is sine. So dv is cosine x dx, and v is sine x. Take these four things, substitute them into the formula. uv is x sine x, antiderivative of v du, antiderivative of sine x dx. Again, because du didn't have a function here, this is now the antiderivative of a single function instead of two, and we wind up with the antiderivative of sine x is negative cosine x. Final answer, x sine x plus cosine x plus c. So what I want you to notice is when you have two functions, if you can get rid of one function by letting it equal u so that the derivative makes it disappear, in the integration by parts formula right here, you only have one function, which we should be able to do. Okay, so the last set of examples takes you through some specific cases. The first one is what happens when you have a single term. Despite the fact there aren't two functions, we can still use integration by parts to finish a single term question. Sometimes, if you start with an x squared, you might have to do integration by parts not once but twice. And then the last one is what's called recursive or substitution. So going in order, the antiderivative of natural log of x, if I let u equal the natural log of x, then du is 1 over x dx. dv is going to be dx. The antiderivative of each side is v equals x. And what you might think is that, well, now I just made it worse. So when I substitute it into my integration by parts, I'm going to have two functions here, this function and this function. But for natural logs, the x and the 1 over x cancel, and you're left with something that you can't take the antiderivative of. So the antiderivative of natural log is kind of a special case because it works out that the reciprocal of x and the x cancel out, and you're left with just this, which is x. So the antiderivative of the natural log of x is x ln x minus x plus c. Second example, what happens if our two functions don't immediately disappear after one application of integration by parts? U is going to equal x squared, but when I take the derivative, that's 2x dx. So you'll notice the function did not disappear. dv is e to the 2x dx. Like we saw earlier, the antiderivative is 1/2 e to the 2x. When I assemble my integration by parts formulas, x squared over 2 e to the 2x is uv. But then over here, like I said, the x squared did not disappear, so we still have two functions inside here. 2 times 1/2 disappears, but I've still got e to the 2x and x. This is just an example of what we saw earlier, so you're going to have to do integration by parts again. So this part gets carried down, the subtraction gets carried down, but you're going to take and do integration by parts again. And this is what we just did on the previous slide, so pretty quick. U equals x, du is dx, dv is e to the 2x dx, antiderivative is this. Assemble your two parts. uv is x over 2 e to the 2x, v du, this times this, v du is 1/2 e to the 2x dx. Now, this is just a single function. The antiderivative is 1/4 e to the 2x. This stays here, distributing your negative, you get a final answer of all of this stuff here. Okay, last one. If you look at your two functions inside the antiderivative, you'll notice here that e to the x will never disappear and neither will cosine x, okay? I can keep taking derivatives of x squared until I get it to disappear. The first time around it's 2x, the second time around it's just 2. But if I keep taking derivatives of e to the x or cosine x, I'm going to get either cosine x or sine x over and over again. So how do we deal with that? Well, you'll see the trick at the end. Set u equal cosine x. I'm going to let dv equal e to the x because the antiderivative of this is very straightforward. So a derivative of u is negative sine x. The antiderivative of e to the x is e to the x. Assemble your integration by parts. uv, e to the x cosine x, minus the antiderivative of v du, e to the x times the negative sine x is plus e to the x sine x dx. And now I see two functions again. So I'm just going to carry this left side down, which was the question. I'm going to carry the partial answer down, and I'm going to take the antiderivative of this using integration by parts. So again, u is going to be sine x, dv is e to the x. So u is sine x, dv is e to the x dx. And the derivative of u is cosine x dx. The antiderivative of e to the x is e to the x. I build my integration by parts. uv, these two multiplied, minus v du, e to the x cosine x dx. And now what I've got is the question plus this first answer plus the next two parts. And if you notice, the original question is now appearing on the right side. So what we're going to do is take this right side and move it to the left side, which means I have two of these now. So the trick with recursive, or when you see two functions that aren't going to disappear through derivatives, is try and get the original question in the answer and then move that question to the other side. Now if I just divide both sides by 2, this is the question, and the right side is 1/2 e to the x cosine x plus 1/2 e to the x sine x. Okay, that's it for part 1 of integration by parts.